Okay, thank you very much. First of all, I'd like to thank the organizers for organizing this very nice workshop. It's been my fourth week here, and I really enjoyed it, so thank you very much. So I'll talk about this long title. I have to apologize for that. There's like not so much or very few actual physics content in this talk. Also, people who know me will be surprised that there won't be, that there will almost be no derived geometry in this talk. So I think that's probably nice. So the plan is to first talk a bit about this relative or constrained critical loci. Then I want to give a large class of examples that come from quiver representations. Then we will further specify this class of example to a single one, which will produce a Lagrangian in the Hilbert scheme. And finally, at the very end, I'll give you a kind of more general perspective on all this. So we'll see that actually there's a kind of non-commutative version of what I've been talking about, like that I will have been talking about in the three first points, and that's where I will talk about Calabi-Yau completions, but that will be the very end. So let me start with this relative or constrained critical loci. So here's the setup. So X is a smooth manifold. So I'll phrase stuff like in the first part in like differential geometric terms. In the second part, I'll move toward algebraic geometry. But first, I think it's better to see what happens in the smooth setting. So we consider the cotangent to X. That's a symplectic manifold with a form, if you write them in local coordinates, that's dp wedge dq. And let's pick a submersion to a base B, so pi is a submersion. Then you can consider the following thing. So that's what I call the relative critical locus of f with respect to pi. So that's the pairs, let's say bxi in the cotangent, such that there exists a point in the fiber of B that satisfies the following condition, that df at x, that's the pullback of psi, right? So you could call this x here a fiber critical point. You may want to call psi a Lagrange multiplier. Sorry? Sorry, that's T star B. Thank you very much. Sorry about that. Otherwise, it doesn't make sense. I agree. Thank you. Right. So the idea is that we want to extremize f under the condition that, so we want to extremize f of x under the condition that px is b, right? So yeah, so there's a way to look at this, which I like. Maybe like some people don't like it. So you have the cotangent to b, the cotangent to x, then you have the pullback to x of the cotangent to b. So that's a submanifold of T star x. That's actually a coisotropic submanifold, and T star b is the reduction of T star x. And what we're doing here is that we have a Lagrangian in X, which is the graph of df. And what we're doing is we're reducing this thing to a Lagrangian in T star b. So we can form the fiber product here. So let me call this crit pi f with a tilde, because that guy is not this one here. I mean, that map may not be an inclusion, right? So the relative critical locus, it's actually the image of that guy inside T star b. right? So there's a proposition, I think, that probably goes back to Harmander, which says that if the intersection of these two guys is transversal, then the relative critical locus is a Lagrangian submanifold. In T star P. I think if you replace transversal by clean, which means that the tangent, like the sum of the tangent does not necessarily generate the whole tangent, but clean means that the tangent of the intersection is the intersection of the tangents. You get probably an immersed Lagrangian submanifold, so it may have like a self-intersections and things like this, but still you get something which is Lagrangian. Okay, I said that I won't be talking about derived geometry, but there's like, just let me mention that there's a fancy version of this. If you ask for no condition at all, and you look at the derived pullback instead of the actual pullback, so you go to the realm of derived geometry. So the derived pullback that you may want to call R crit by F. R is for derived, obviously. That's just a joke. That's a right derived functor. So if you compute that fancy object, then it has a map to T star B, and this map is a Lagrangian morphism in the sense of derived symplectic geometry. But I won't be using that. That just I just mentioned it for the record. Okay. The intersection of these two guys inside T star X. So these two things are submanifolds. So this pi star T star B and X, and the graph of df in T star X should be transversal. In this case, you get the image of this map is Lagrangian. All right, let me give an example that might speak to people who like physics. So let's take M, a manifold, and let's assume that we have a function, a Lagrangian, that goes like from R cross Tm to R, so it's a time-dependent thing. Now let me take as X, so that's where I'm going to get out of this context because I'm taking X infinite dimensional space. So it's going to be the space of path from 0, 1 to M, sorry. And as a B, I'm going to take M cross M, and the map down here, that's evaluation at 0 cross evaluation at 1, so evaluation at endpoints, right? And as an F, let me take the usual thing. It's integral from 0 to 1 of L T gamma dot T dt. So that's the usual action. And a curve in there, so a gamma is a fiber critical point. Well, that's a very standard calculation. That's the same thing as saying that gamma is a solution of Euler-Lagrange equation. And but if we now want to characterize the image in here, so let me have a restriction to a specific situation. So let's assume that the Legendre transform is a DFO. So that's this thing that sends x dot to x y, where y is the derivative of the Lagrangian. So assume that we have this. So In this case, then we get a Hamiltonian. Well, it's a time-dependent Hamiltonian. You can, like that gives you a Hamiltonian vector field, so you can integrate it. So we have a one-parameter family of symplectomorphisms of the cotangents to M, right? And in this case, the relative critical locus is just the graph of the time 1 symplectomorphism phi 1, right? So that leaves in T star M cross T star M. There's a little thing you have to pay attention to, actually, like one of those has like reverse. It doesn't matter so much because for cotangent, T star M and T star M with the opposite symplectic form are diffeomorphic. You just like revert, like you multiply by -1 in the fibers, you get this. And that's just the fact that the graph of a symplectomorphism, it is Lagrangian in the two copies of a symplectic manifold. So it boils down to something very easy in this case. All right. Yeah. Yes. So like I don't know how to like you can prove that it defines some kind of isotropic things in a generalized sense. Checking like that it half dimension, it doesn't mean so much. I mean, well, even though in this case the base is finite dimensional, so like in good situation you can just check in an ad hoc way when you have a nice description of your relative critical locus that it is indeed Lagrangian. But I don't know a general theorem that would work in like when you have infinite dimensional things involved. Sorry? No, the function f is this thing here. But you can rewrite it as an integral of like a pdq minus h somehow, like minus h dt. I think this function f in this case, it's like I don't know, something of that sort, I think. It's just like you go from like a Lagrangian to Hamiltonian description of your functional, but yeah. All right. So now I want to show you a large class of example of this situation that comes from a representation theory of quivers. So let me just say that a quiver is just a pair VE, where V is a set of vertices and E a set of edges. So it's just an oriented graph with a finite number of vertices and finite number of edges. And I'm going to fix n a dimension vector. So that's just a collection of numbers at every vertex. So that's we have integer at every vertex, right? So no, like that's quiver, that's this data, and now I'm specifying a dimension vector. So I'm getting interested in representations of quiver, and I have to fix the dimension of the vector space on which I act. So that's additional data. Okay, and the space of representation. So that's a vector space actually of representation of the quiver of dimension vector n. That's a collection of matrices. So for every edge, we have a linear map. So let's work over C, so that we have a linear map from C to the source of the edge E, from C to the source to C to the target. So, sorry? Yes, so that's n of this, right? Exactly. Thank you very much. So here, whenever I have an edge, I just write S of E and T of E for the source and the target of this edge. And I want my map to go from a vector space of dimension n at this n of S of E and to n of T of E, right? Okay, now, so that will be, like, that will play the role of X. Now, if I want to construct a function on such a space, there's a very nice way of doing this. We can pick W, a linear combination of oriented cycles in Q. Like, there's another way to reinterpret that. That's an element. So we take the path algebra of the quiver, the path algebra generated by all edges, and whenever, like, so we just have path, and whenever you multiply path, if they are, like, if they start and end at the same point, so that you can concatenate them, it's just a concatenation. If you can't, the multiplication is 0. Modded out by commutators. I want to insist on the fact that this is not an algebra. It's just an algebra modeled out by a vector space. So CQ, that's the path algebra of the quiver. So it's you take just a path in your quiver, and the multiplication is concatenation whenever you can concatenate, 0 otherwise. Other people would say that if you want that, you can view it as the free category generated by this data, because in here, in a quiver, you don't have a multiplication of arrows. CQ, you could view it as a category freely generated by this. And but I prefer right now to view it as this just path. Sorry? You just take commutators of those things, like AB minus BA. So you just take the vector space of commutators. And it's like, it's not a quotient by a two-sided ideal, so that's not an algebra, it's just a vector space. But if you want a concrete description, this thing is equivalent, like it's described as all possible linear combination of oriented cycles in Q. So that's what it is. And now, whenever you have something like this, what you can do, you can define a function on X. It picks some representation, and what it does, you evaluate your representation on each of these cycles, so it gives you an endomorphism of a given vector space, and then you take trace of this. Of course, a priori, it depends on the base point, so you have a cycle, I don't know, like this in your quiver. So start with here, you take the representation, so it gives you a map from here to here, you compose and you get back, it gives you an endomorphism. You take trace of this. You might argue that this depends on the point you've chosen, but trace is conjugation invariant, right? So it doesn't matter which point you choose to do this computation. So that defines functions on the representation space. Right. So now, what I want is an analog of the base B. And if you look at the example that we have here, so there's a large class of example, still infinite dimension, that you could write that generalize this. Is you have a field theory, like on a worldsheet, you have your action functional. Assume that your worldsheet would have a boundary, and somehow, like, you have the fields on the bulk, and the map pi is restricting to the boundary, and that's a typical situation you might have in field theory. So what I want to do here is kind of do a kind of a purely combinatorial analog of having a boundary. So I don't know what's the boundary of a quiver. So the only thing I can think about is taking a subquiver, right? So I'm fixing a subquiver D inside Q. Subquiver means like you have a subset of vertices and a subset of the arrows. You have to choose them wisely so that the endpoints of the arrow of the subset of arrows lies in the subset of vertices, right? So I don't know. That's a subquiver, for instance. Okay. It doesn't like in here. Oh yes, that's also a subquiver. It doesn't have to be full, right? Absolutely. And you'll see that the main example I will be interested is not full. Okay. Now, so I have X, which is representations of Q of dimension n, and then I can restrict to B. That's going to be representations of D of dimension vector M, where M is just the dimension vector n restricted to the vertices of D, right? Okay. So, like in general, we can definitely do that. So we have this, and then we have the function trace of W. And so we are in the situation where we can study this relative critical loci. So let me give an example of this class of example that will be of interest later on. So the example is a fairly simple one. So both quivers will have only one vertex. The first one, Q, will have 3 loops that I'll write X, Y, and Z. And the first one will have only one loop, which is X. So that's D, and that's Q. All right. So there are reasons why I'm doing this. If you know a bit about the Hilbert scheme, that's that's things people have seen already. So if you take not the relative, but you forget about D and you take the absolute critical locus of this function here for this choice of Q, you end up constructing with some additional things. So if you add a framing and you put stability condition, then you end up finding the Hilbert scheme of points in C3. And because it's a critical locus, you know that it has a nice derived enhancement that's going to be -150 symplectic. Then it means that it has a symmetric obstruction theory, and you can start talking about DT invariant and stuff. So that's one thing you could do. This one, if you double it, meaning that you go to some kind of cotangent and you repeat a similar story, you end up getting the Hilbert scheme of points in C2. So I'm choosing on purpose something that kind of like is intermediate between these two to just try to find some Lagrangian in the Hilbert scheme in C2, right? So that's why I'm taking this specific choice. But we're not there yet. So as a W, let me take XYZ minus YXZ. So that's a very standard potential. That's the one that gives you the Hilbert scheme of points in C3. It's just like when you take derivative of this, you get commuting relations. So representation of this, that's just 3 matrices. And now if you take the derivative of this potential, it means that you have like a commuting matrices. And if you go to their joint spectrum, you'll start to see something that looks like a triple of eigenvalues. And when you resolve this, you get Hilbert scheme. Anyway. The dimension of the representation space? Oh, sorry. You just fix n. There's only one vertex, so you just fix n, right? Later on, I'll add a framing, and the vertex for the framing will be dimension 1. But we'll see that in 10 minutes from now. Okay, so now we can consider the critical locus associated with this. So let me give it a nice description, or an explicit description. So if we compute it, what we find is we have pairs of X and Lie bracket of Y and Z, where X, Y, Z are just n by n matrices. And we have the condition that y commutes with x, and so does z. And that's it. So that leaves in two copies of the space of matrices, but using the trace form, you can identify this with a cotangent, right? So that's what it is, and we, like, even without knowing anything about critical loci or whatever, you can check that this is Lagrangian submanifold in here. So that's a little lemma. I mean, sorry, subvariety, and it's not smooth, but all its irreducible components are smooth and Lagrangian. So that's the, yeah, so the lemma is the following. Thank you. So lambda n is actually a closed subvariety in T star M and T. And its irreducible components are so smooth and Lagrangian. Let me say that you have to be smooth to, like, so that you can talk about being Lagrangian, otherwise it doesn't make so much sense. Well, it's of pure dimension. Well, it has to be half of the dimension, so that's n squared. And then there's also something that you can say is that the irreducible component, they are indexed by, I'm losing my words, partitions of n. Okay. Right, but that's not what I'm interested in, because like all this is, it's essentially linear algebra, right? I mean, we're just taking a bunch of matrices and we're playing with them. At some point I want to, like, there's way too many variables here. We have n squared. So I want to mod out by the action of GLN. So that's what I'm going to talk about right now. Before doing that, let me mention that set theoretically, so that's something that might, if you know a bit about Lie theory, that might convince you that that guy is interesting. This lambda n, so that's something that was actually suggested to us by Michel Vergne, who, when she saw this, she told us that it should be true. And then Tristan Bozek could prove this with Anne Moreau. I don't think they've written this yet, but like they check it, it's correct. So set theoretically, lambda n, it's a union of conormal bundles to subvarieties that are called Dixmier sheets of GLN. Dixmier sheet is what? These things are, so they are irreducible components of the following subvarieties. So these are, so GLN K, for K an integer, that's those matrices that are such that the dimension of their orbit is precisely K. So this defines subvariety into GLN. They have irreducible components, and that's what people call these Dixmier sheets. And they are, I mean, they seem to be, that's something you can define for, so for every Lie algebra. Actually, notice that this is also something you can define for any Lie algebra. If your Lie algebra comes with a symmetric non-degenerate pairing invariance, you also get that the pair G cross G is the cotangent. And in general, you can wonder if you can still define this Lagrangian, if this Lagrangian is also a union of conormal to the Dixmier sheets, and I think this is not true in general. That's true for GLN, that's true for SLN, but like these DXMA sheets, it's like, apparently there's a whole industry about like computing them, finding their dimension and stuff, and like out of usual types, I mean, it can get complicated. But I don't know much about this. So. All right. So now, let me move on to the main interests I have is this Lagrangian in the Hilbert scheme of n points in C2, sorry. So, okay, so here is the story. So let me tell you what is the Hilbert scheme first. So what we can do is consider the symmetric powers of C2. So C2 is a symplectic vector space. What is this? It's just C2 to the n modded out by the action of the symmetric group. Of course, this is a singular space. The symmetric group does not act freely on it has isotropy, so you have jump of dimension, so of the fixed points. So this is a singular space, but on its smooth locus, it has a symplectic form that comes from the symplectic form of C2 to the n. And there's a nice resolution of singularity that is symplectic. So there's a space, which is the Hilbert scheme, which is a symplectic resolution. Okay, and there's a very concrete way to actually construct yes? So there's a kind of canonical algebraic symplectic structure that you can construct, but of course it happens to be hypercolor, and then you have a whole bunch of symplectic structure. But I'm talking about the one that you get when you do the construction within algebraic geometry without appealing to complex analytic geometry. So somehow I agree that there's a P1 of symplectic structure, I think, but there's one which algebraic geometers would prefer, I would say. That's the one I'm talking about. It's an algebraic symplectic variety. So like it is also a holomorphic symplectic variety, and then it happens to be hypercolor. So
no, but I'm just trying to clear out the terminology. So you're talking about 2,0 symplectic form on hypercolor.
Yes, and 2,0, and they are holomorphic, so they are closed by d bar, right?
Because whenever differential geometers say symplectic, it's here.
Oh, sorry. Yes. So. Thank you very much. That's a very good point. So it's true that in the first part, like in part 1, I was talking about differential geometry. When I moved to part 2, I said it before, but then I didn't say it again. Like I'm moving to algebraic geometry. So all what I'm saying is now all my symplectic structure, I mean algebraic symplectic structure. So like if you go to complex geometry, that's holomorphic symplectic. So 2,0 and d bar closed additionally. Okay. Yeah, so we have this symplectic resolution, and there's a construction. So there's an explicit construction using quivers, which I think is due to Nakajima. And that's probably where, in some way, it connects back to physics, but in a way that I don't understand. So I won't say anything about it. So here is the construction. So somehow, the Hilbert scheme, it's a kind of a twisted version of a cotangent bundle, and it's a cotangent to a quotient, like representation space modulo GLN, and cotangent of quotients. They are known to be symplectic reduction of quotients. So here is the setup. So we have now D. Our quiver will be the same thing as before, but with a framing adding. So we have a quiver of that type. And the dimension, so that's the first vertex and that's the second one. And the dimension vector now is 1, n. So we just put a one-dimensional thing here and still an n-dimensional thing here, right? And we're not going to act by all symmetries. We're only going to act by GLN here. So we don't act by rescaling in here. We don't want to do that. So we look at the action of GLN on RAP dn. And so if you want to compute the cotangent to the quotients, you might want to do Hamiltonian reduction. So we are interested in the cotangent to the quotient RAP dn mod GLN. And there's an arrow here and no arrow here. That's just not the full symmetry group, just GLN. All right, so the general idea is the following. You have like a group G acting on M, and then you're saying that T star of M mod G is a symplectic reduction, where the moment map is defined the following way. So you have x psi, and you send it to a form, linear form on G that sends y. So y is an element of G to what? To psi paired with the vector field associated with the element in G, but at x. So that's this, right? So that's a moment map. Of course, this thing here, this is a bit sloppy because like you have to have a lot of conditions for this to work. I mean, like the action should be nice, maybe 0 should be a regular value, all these kind of things I'm right now ignoring. But that's the general idea. So if we want to construct something that looks like this, we should do something of that sort. So let's do that. All right, so first of all, let me observe that, so we have the cotangent to the representation of D with dimension vector n. Let me just observe that this is the same as the representation of the double quiver with the same dimension vector. So the double quiver is you keep the same vertices, and to every arrow, you add a new arrow that goes in the opposite direction. So for our quiver here, we had x, and we had u here, for instance. Then you add an x that goes the other way around, and so that's x star, and you add a u star there, right? And if you look a bit at what the moment map becomes, it's actually a kind of commutator. That's a computation one has to do. But so in the end, the moment map mu, in this very specific case, it goes to GLN, which is the same as its dual. Let me point out that here, I've been taking the action by GLN here, so I'm only acting on that part. So I will not only, like I will have a commutator for this, but only a product here and not the full commutator. So what I'm ending up having is that I have x, x star, u, u star, and I'm sending it to the bracket of f, x, and x star, plus I think that is, what is it? I should write it in the correct direction. U, u star. So you have like, that's not the scalar products. So we have a line and a column vector. If you multiply them in one way, you get a number. If you multiply them the other way around, you get a matrix. That's the matrix of products of all coefficients. That's what we have here. We want a matrix here, right? And well, one can show that's exactly when you get, if you consider these quotients in this specific situation. So now it means that we're interested in representation of this, of the path algebra of this quiver modeled out by this relation. So Actually, that's what people call the preprojective algebra. We don't need to know about this, but it has a name and it's been studied a lot in representation theory. But the upshot of the story is that the Hilbert scheme of points in C2, it's the following thing. So it's mu inverse of 0. There's a little thing here, modded out by GLN. And this little thing here, it's a stability condition that you put so that the quotient is nicely behaved, right? Because otherwise you might have... Yes. Yes. I know that's not. Yeah. That's. I'm doing like GIT quotient if you want. So in really holomorphic or algebraic geometry. Again, yeah, I agree. I think the reduction for algebraic symplectic varieties, if you go to complex points, it bears some relations with hyperkähler reduction. But it has to do with the hyperkähler reduction with respect to some like compact subgroup of some real form. I don't know. I know that there is a relation between the two. I'm not knowledgeable enough to tell you what it is, but there is a relation, yes. All right. So yeah, this stability condition here, it's just saying that U is a cyclic vector. So if you start from the vector U and you act by the matrices X and X star on it repeatedly, you will generate the whole representation, the whole vector space, like Cn, okay? So like that's just a condition that we put so that the quotient is well behaved. And that's a way to define that's one way to construct the Hilbert scheme. So it's a kind of, you can think about it as a kind of cotangent to the quotient. It's not exactly, it's rather a twisted version of this, but yeah. So now, as before, we can repeat what we've done before, and we have the very same Lagrangian inside here. So let me, I erased precisely what I'm going to rewrite, sorry. So we still have this lambda n, let me write lambda n comma 1 because we have now this framing. That's the same thing as before almost. We have x, we have brackets between y and z, we have u, we have 0. So the conditions are that still u is a cyclic vector, and that yx is equal to 0 and is equal to zx, right? So that's something, and then so that's something you can prove that lives in the zeros of the moment map. Well, that's fairly easy because of this commutation relation, this commutes, and u times 0, that's 0. So it's in the 0 of the moment map. So we mod out by GLN. And so that defines a subvariety. So it defines a subvariety in Hilbert and C2. This subvariety, it's not quite what we want yet. It has this problem that is not saturated by this map. So this map has a name. It's called the Hilbert-Shaw map. And so if you take this subvariety, you map it there, and you take its pre-image, you get something bigger. And that's why I'm going to be interested in. So the theorem is the following. So we define Ln to be HC inverse of HC of this lambda. So like what it has. So it has smooth Lagrangian irreducible components. Well, of pure dimension n, but well, it's Lagrangian, so it has to be. and its irreducible components are indexed now by nested partitions. So it means that you have a of n. So it means that it has a lot of irreducible components. So it means that you pick a partition of n, you have numbers, and for each of these numbers, you pick an additional partition. So here is a nicer description of Ln. Whoops. Which does not appeal to the Hilbert-Shaw map. So Ln, you can describe it in the following way. So that's, you have, right, so x squared, u0. We still have that, we want x and x star to commute. We want u to be a cyclic vector. And then we want an additional condition, which is saying that whenever I take x star, so it stabilizes any generalized eigenspace of x just because x and x star commute. So I restrict x star to any generalized eigenspace of x. The trace of this must be 0. So that's the thing that we have. So that's I think a much nicer description than this thing which like you might not have control on, like when you saturate it with the Hilbert-Shaw map. There's another thing that you can see. If you take it's imaged by the Hilbert-Shaw map, this has a very nice description. It's a union for any partition of n. So let me see how I'm going to describe it. So you get something of that sort. So you get, so we have like, so we have like classes of n tuples of pairs of elements that you have to think of them as the joint eigenvalues of your pair of matrices. And so how is it? So for every of those partitions, you will select, so typically you will have like a, I don't know, you will have equations like you have L, A lambda, I don't know, K plus 1 equal up to A lambda of K plus 1. So you have a partition, so a bunch like in each partition, all the parameters, all the eigenvalue of the first matrix should be the same. And then we're taking actually the conormal to this condition, so which means that for the other, it's just the sum of the same things that should be 0. So these are actually conormal to some guys. So it's kind of like if you know there's another Lagrangian like which is very canonical in the Hilbert scheme. It's the Hilbert-Shaw saturation of the thing where you have all the b's being equal to 0. So you just take half of the variables. That's called Lustisch Lagrangian in the Hilbert scheme. This one is very different. It has like way more components somehow. Yeah. So the symplectic form on the smooth locus, that's sum of dAI, dBi, right?
No, it's just that when you have a partition, the order of the parts is not defined, but you've chosen an ordering.
Yeah, I agree. So like, but you have to check that this is compatible with like permutation. So somehow I'm just saying that on the level of that's a kind of cheap way to translate this condition here. So somehow, like you first select the eigenvalues there, and you have this condition here, this trace condition that gives you actually this.
Are we pushing by Sn, for example?
Oh yes.
Oh, sorry.
Yeah, sorry. Yeah, that's. Yeah, no, of course, like that, yeah, you're right. Yeah, we're quotienting that by Sn. Yeah, sure, of course. Sorry, thank you very much. So here's, like, I would have two questions, maybe for you or in general, about this. The first question, we've looked for it, so if anyone knows this Hilbert scheme, so we've asked a lot of people, and have you ever seen this Lagrangian anywhere appearing? That's our first question. That's a cheap question, but there's a nicer one, which is, so yeah, I'll say it in words. So there's this whole story that there's this nice algebra, which is called the rational Charonic algebra in type A. And to any representation of the rational Charonic algebra, you have a characteristic variety construction or characteristic cycle construction that produces a Lagrangian cycle in the Hilbert scheme. So now there's a very nice characterization of the category O for this rational Charonic algebra. It's those representations whose characteristic cycle belongs to is a combinations of components of Lustig Lagrangian, the one where you have like all the b's being 0. So the question is like, is this like, can we characterize those algebraically, those representations whose characteristic cycle actually belongs to irreducible components of this? I have no idea. Like, I'm just like incompetent in representation theory, so I was not even able to produce one representation having like its characteristic cycle living in there. I just don't know if actually they exist. I would guess yes. So there's a bunch of things you can do. I mean, you can check to be a candidate to be the characteristic cycle of someone. A Lagrangian satisfies a bunch of necessary, maybe not sufficient condition, but necessary condition. And this Lagrangian satisfies all of them. So I've asked Pavel Tingov, he gave us like a criteria, which is, again, that's necessary, it's not sufficient. And we check that, so that's a good candidate for being the characteristic cycle of something, but we couldn't find any representation that leads to this. So if you know anything about it, I'd be interested. All right, so I'll move on to the last part. How much time do I have? Sorry? 7 minutes. Oh, wow, that's very precise. Thanks. Sure.
I should not ask this question until
Sure, you can.
coffee. So you have nested partitions.
Yeah.
I'm curious if do you have a pair of maps to something which just depends on one partition? If you forget either the outer partition or the inner partition.
No, not that I see. It's a good question. I don't know.
So I'm thinking maybe there's a vibration to the nerve.
Okay. I never thought about it. I'll give it a thought. Yeah. I'll think about it. I don't know. At first, I would say it doesn't seem so, but maybe just that I didn't think about it enough. Okay, so here is a more general perspective. So all what I told you about, that's just like one section of the paper. That was the kind of the motivating section of the paper. The whole paper is about Calabi-Yau structure and derived symplectic stuff. So if you're interested in this, just read section 3 of the paper, and that's all you need, and there's nothing derived there, just like a symplectic geometry in the algebraic context. Okay, so the first observation is that all what I did, like which could seem very geometric, actually all the construction have non-commutative algebraic counterparts directly on the path algebra of the quiver. So all constructions are purely non-commutative, and then we just apply some representation functor. So that's the nice thing. For example, if you think about the moment map, the moment map is just this map that goes from the polynomial algebra in one variable to the path algebra of the double quiver that sends X to sum of like E star minus E star E. That's a kind of non-commutative moment map. And essentially, the Hilbert scheme is a kind of representation scheme or representation space for the quotient of this algebra by the ideal generated by this, which is what people call the pre-projective algebra. So we have like a CD modded out by this relation. That's called a pre-projective algebra. And there has been a slogan in people doing like this non-commutative symplectic geometry. That's the pre-projective algebra is the correct non-commutative cotangent. And there's a lot of hints that this should be true, and the whole point of our paper is to prove that this and several other statements are actually true if you go to this derived setting with Calabi-Yau structures. So I'm not going to explain everything, but yeah, I want to explain one thing. First of all, the one thing you should do is to introduce a derived version of this. So instead of taking the, well, in quotes, stupid or zero truncated quotient, you just compute the homotopy quotient of this. It's just a like silly thing that you do. Instead of putting this relation, you just add the generator in degree -1, and you say that the derivative of this, the differential of this element is the relation. We're doing nothing more than that, right? So we just, what we do is you add a new variable, non-commutative variable, let's say x of degree -1. Let me call it x bar, and we add the condition that we define the differential to be dx bar is the value of the non-commutative moment map. Okay. So that's what people call G2 of the path algebra. So it was first introduced by Ginzburg. Thus, this is called Ginzburg algebra. And then it was generalized to like DG categories by Bernard Keller, who called them, in the general context, he called them Calabi-Yau completions, because they are Calabi-Yau, and they kind of satisfy some kind of universal property among Calabi-Yau things that receives the map from CD. So the theorem now that I want to state, and I'll end with this. Not really, because it's a non-commutative variable, so like it does not anti-commute with itself, right? So, yeah. So, I mean, you could say it's a non-commutative Grassmann variable. It's a variable of degree -1, but it's not a, strictly speaking, it does not satisfy the relation you would expect. Yeah, there was another question, no? It's the property of the algebra, so like, yeah, there's several notions of Calabi-Yau. So I'm using what Brav and Dikharov call left Calabi-Yau. That's the Calabi-Yau condition or Calabi-Yau structure for smooth algebras. So those things which are dualizable as bimodules, not as k-modules. So it means that you can view the Hochschild complex as a derived map from some dualizable module to A, if A is your algebra. And then like, well, I don't want to define, but like that's if you look for this in the literature, that's what people now call left Calabi-Yau, or that's Calabi-Yau for smooth algebra. And when I say smooth, I mean homologically smooth, not in the strict sense. So the theorem, and I'll end with this, that we proved with Tristan and Sarah. So that's only one part of the story. There's analogs of this theorem for relative Calabi-Yau completion and critical loci, but I'm going to state it for the cotangent. You can imagine like add relative, twisted, all adjectives you want, this theorem will still work. It says the following: if you take the derived stack, that's the only place, that's the final thing where I'll say these words because I have to say them. So we take the derived stack of perfect representations of this algebra. That's equivalent to the cotangent to perf of the path algebra as a, well, in this case, zero shifted symplectic derived stack. So this guy perf, it's a super fancy enhancement of the following functor that takes representation and take the quotient stack by the action of GLN of symmetries. Now you're allowing for representations which are complexes of representations. And there's like Toine and Vaquier constructed this and show that it's a nice geometric derived stack. So that's the theorem. It's a theorem saying that the philosophy that this preprojective algebra should be the non-commutative cotangent. That's actually really true once you go to the derived setting and you take perf instead of just representations. And I'll be done with this. Thank you. Right, this ALE space or?
Right, for example, Nakajima was interested with the resection of Heisenberg from homology, etc. Do you know any significance of your Lagrangian
No.
in this context?
So what I know is that like a nice feature of the Hilbert scheme is that it has some factorization properties that are really useful when you start talking about whole algebras and this kind of things. This Lagrangian satisfies all the same properties. So it's also like something that has some factorization property. But I don't know how much it's relevant for like this instant on things or like, I know that this Nakajima curve variety, they also appear in this Coulomb branch of this like conjectural, when you do this dimensional reduction for this 6D n equal to supersymmetric field theory. I don't know if this thing has anything to do with that. I'm just like, we ended up like, we have like, the true story is that we were interested in derived geometry at first. We had this relative critical loci, we were happy about it. And at some point we wanted to see if it would lead to some interesting construction in actual algebraic geometry so that we could go back from derived to like real things. Not in the sense of real geometry, like just more concrete stuff. And we ended up like doing this construction for Quiver. And we were looking for something, as I said in the beginning, that was kind of in between this Hilbert scheme of points in C2 and Hilbert scheme of point in C3. So we ended up finding this. We looked in the literature if there was something similar. We didn't find it. And then we asked around people, like, do you know this? And the answer was always no. But the true thing is that I don't know what to do with this Lagrangian now. It's there, but I don't know if it's really interesting or not. I don't know. I don't think this Nakajima construction is kind of compatible with Quiver mutation. So I think if you do Quiver mutation here, it will completely change the geometry of representation space. So maybe it will change the geometry in an interesting way, but not in a way that I know how to control. Yeah.
When you cited 400 at the beginning, Lagrangians
Yeah.
appear as wavefronts of integral penetration.
Yes, exactly. Yeah.
Is there something that would correspond in that spirit to these Lagrangians?
I think the only thing that is close to answering your question is really asking if these Lagrangian or some of its irreducible component appear as characteristic cycle of some representation of some algebra that kind of look like differential operators. Because like there's this usual story, if you have a D module, it has a characteristic cycle that's a Lagrangian, that's coisotropic in general, but if your D module is holonomic, that you're gonna have a Lagrangian. And then there's this more recent thing that people notice that's, so the rational Choroinic algebra, it looks very much like an algebra of differential operator. It's not, it's generating by things that are called Dunkel operators. And it has a characteristic cycle construction that end up having its thing not in a cotangent, but in a kind of twisted version of this cotangent, which is the Hilbert scheme, right? So the closest thing to what you're asking for is, I think, this second question I had, and I don't know the answer. I would love to see just a single representation of the rational Choroinic algebra whose characteristic cycle belongs to this Lagrangian.
But if there was some kind of operator differential or whatever, would it have a presentation in the quiver slide?
Oh, I don't know. Yeah, this I doubt a bit because I don't know. I don't know, but it's just that like the Choroinic algebra has this very nice feature that it's triangular, so it has a triangular decomposition. You have let's say essentially you have P and Q variables, and in the middle you have the group algebra of the symmetric group that sits there. It kind of plays the role of the Cartan. It's not commutative, but and you can talk about highest weight module and these kind of things, and that's how you construct the category O for the rational Choroinic algebra. But definitely the category O, just because you start from something that acts trivially on one part and then you induced, it's pretty obvious that it will end up having something with where the characteristic cycle will have something which is like 0 on half of the. Like if you want to cook up representations which are more mixed that satisfy these kind of things here, like you have to come up with something more complicated. So maybe you might want to induce from representation from like GLN cross GLM into GLN plus M. You might have like some Gelfand settling stuff. I have no idea, but yeah.